All right, good afternoon, everybody. So this is going to be lecture 20. It's going to be a little bit shorter than some of the other lectures in the Star Tracker unit, which is good because I think we could all use a little bit of a break. And this is going to be on star identification. So let me go ahead and share my screen, and I'll bring us back to the lecture notes from 2 lectures ago, where we outlined basically the whole unit in 4 pictures, right? So there's 4 things that you need to have working in order to have a functioning star tracker. The first is a space camera, and we model the physics behind how light from stars becomes pixels in an image. And if we understand that mathematical model, we can work it backwards and say, oh, these pixels in these images tell me that there are stars in these directions in front of me, which is great. So you have local star directions. You also have global star directions, which you can build from a star map. And we use astrometric parameters, which are gathered from astronomy missions, essentially. And those astrometric parameters allow us to get the star line of sight directions in a global frame. And if you have the same line of sight directions in a local frame and a global frame, you then have an attitude estimation problem, which is next lecture. But we skipped a step. If you have the same star line of sight directions in the local frame and the global frame, how do we know it's the same stars? How do you know that these 5 stars in the image are, star A, star B, star C, D, and E in the catalog? So the star identification problem is one that's easy to gloss over, but it is probably the hardest to implement. Like, I think when the time comes for y'all to sit down and code this up, this step and the contents of today's lecture is probably going to be the hardest. By contrast, next time's lecture, lecture 21 on Waba's problem, attitude estimation, is going to be page after page after page of math, but most of that is derivations. And when you're done, you can solve Waba's problem in 3 lines in MATLAB, right? So that's going to be pretty straightforward. I think today is going to be where a lot of the struggle comes from. So now's a good time to really pay attention and dig in. I hope that y'all have gotten a start on homework 4. Maybe you're even at the point where you have star line of sight directions in the local and global frame. That would be fantastic. Next is the star identification problem, which we're going to go over today. So we'll start with a quick discussion. And I'm going to take a volunteer in just a minute here. So whoever's feeling brave, now's the time to get your gumption up. In order for a measurement to be useful for navigation, we must know what we're measuring. Here, make a little more room here. We must know what we're measuring. So this could be obvious if you're, say, leaning out the window and taking a picture of the Earth. That's the Earth. It doesn't take a rocket scientist to identify the Earth. Although identifying the Earth in a digital image with no human in the loop actually becomes a pretty tricky either classical image processing or machine learning neural net type problem. When it comes to identifying stars, thankfully, we do not need neural nets or machine learning. As navigators, while those technologies are very exciting and new, they are exciting and new, and we like navigation to be boring and solved, and any fancy exotic navigation technique would not be part of the critical pipeline that keeps the astronauts alive. We want it to be nice and simple, right? Engineers in general strive for simplicity. So we're going to talk about the simplest possible way of doing star identification. So in the case of stars, we seek to correlate image stars to catalog stars. All right, so I'm going to draw 4 pictures here, and I'm going to take 4 different volunteers. There's going to be a lot of class participation here. So people who are feeling brave, now's a good time. Let's see here. Just let me get my windows open. These are going to be 4 different star field images. Here comes my basic rectangle drawing skills. And last one. Okay, so who's my first volunteer for an open-ended question that you don't know what I'm going to ask yet? We'll see who's feeling brave today.
I'll try it.
All right. So Renee, apologies, but this first one is an unanswerable question. So you really stepped on the landmine there. So
Okay.
my question is, here's your star field image. What star is that?
With a single star,
Yep,
I do not believe we can answer it with just one star.
good. All right, so because you were so good, let's try this. Which stars are these?
I'm still not certain that we could answer that.
Okay. You know what? It might be easier. I think it might be easier to just go through this whole thought experiment with one person. So just keep bearing with me here. All right. Okay. Which stars are these?
So now I think we could at least make a guess. I don't know how reliable it would be.
Okay. What would be your logic for coming up with a guess?
Um, so we could s- we could look at the angles between them. Uh,
Aha. Okay.
right,
So we actually have some data here. I'm actually gonna write more data because we do have some data in this image.
right. But I'm recalling the triangulation problem, and wouldn't we need four?
Ooh, okay. So you're already going somewhere pretty cool. Okay. So I'm just going to start by saying there is essentially one piece of information in this image that is useful for star identification, and it's going to be one angle, the angle between the two stars. Whereas this one has three angles. Would you agree with that? We've got the angle between star I and J and K, and then K and I. So we've got three pieces of information in this one. Now, what about this? Here comes my best art. That's the best I could do. Can you identify those stars, Renee?
I'm fairly certain that's Orion.
That's supposed to be Orion. Yep. Okay, but how did you do that? Because you did like this was me, my art skills, trying to draw five dots, and yet your brain figured it out. How'd you do that?
Because of the belts, because it's very recognizable.
Yeah, it is a recognizable constellation. Very good. Okay, so thank you for being my participant through this thought experiment here. And actually, it turns out that in all three of these cases, we have at least a prayer of trying to identify the stars. It's definitely not possible in the first case. And we're going to talk about just exactly how many stars you need. There's how many stars you need mathematically, and then there's how many stars you need practically. And those are two different questions. But very good. So thank you for your assistance on that. So in much the same way, here we go. In much the same way that humans recognize constellations, rather than individual stars, it is possible to recognize, I'm going to put quotes on that because computers can't recognize anything. It is possible to recognize an asterism or group of stars. So, what is it? All constellations are asterisms. Not all asterisms are constellations. So, you could think of a constellation as an asterism that has a name, but you could pick literally any group of stars because they are a group of stars. They are an asterism. So, group of stars in a star field image. So we don't go for stars, we go for groups of stars. And we've already kind of alluded to our main tool for doing this is the angles between the stars. Right? Now, there's a reason why we use the angles, and we're going to get to that in a second here. So this identification problem, this requires an asterism descriptor. So this requires an asterism descriptor. And that asterism descriptor or descriptors must be invariant, that is not variable, invariant to changes in observer state. And then I'm going to write attitude in particular. Okay. Particular. I remember how to spell. So what exactly do I mean by that? So we need there to be some numerical name tag that we apply to every asterism. And it needs to be that if we take an image of those stars, of that asterism, we would compute that invariant from data in the image, no matter how we look at it, right? No matter how you look at it. Because you might say, okay, well, let's go back up to this diagram of two stars here. We're looking for one star that is over here and then another star that is down and to the right a little bit. But if we were upside down, that's different. But, the other one would be the other way. We need it can't be based on their position in the sky because you don't know where you're looking. You just have a star field image with dots in it. So it needs to be something where whatever your camera attitude is, wherever the stars show up in the image, there is something about them that is invariant. And we've kind of already let that slip. It's the interstar angles. So the angles between your stars don't change. You might say, well, why don't we use the number of pixels between the stars? It's like that's actually something different. The number of pixels and the angle between them are two different things. And that comes down to distortion, right? It comes down to distortion and just the physics of pinhole camera projection. So what we like to do is we work with line of sight directions to stars, not with their pixel coordinates. Because you can imagine as we, move these two stars to the edge of the image, their line of sight directions are going to start to get warped. One of them is going to be more warped than the other. So we don't like to do star ID in pixel space. Also because if you go back to lecture 18, there are no pixels anywhere in our discussion of star maps, right? We are working with line of sight directions. And so the relationship between line of sight directions or the angles between stars, those are invariant. Even if your camera is upside down and backwards, even if you teleport to Jupiter, the stars are going to look about the same. They're not going to shift that much due to parallax, right? So we're looking for something about the stars that won't change, and we're going to use interstar angles. So these asterism descriptors, or these numerical name tags, are called invariants. And they can be thought of as numerical name tags. Numerical name tags. And as per usual in this class, I talk faster than I write, so now I got to catch up and say things that I've already made points about this. So the question, what about an asterism is constant no matter how you look at it? And it definitely can't be anything about pixel count. Or the shape of the asterism in an image. Because those can be warped. If we have two stars, we have one interstar angle. If we have three stars, we have three interstar angles. And so Renee very adeptly brought something up that I didn't even ask about, and it was exactly how many stars do we need before we have a unique solution? I believe her guess was four. So we're going to address that in a second, but that is exactly the way that you should be thinking as a spacecraft navigator. Start thinking about degrees of freedom, how many pieces of information that we need, how many pieces of information do we have, what is unique about this measurement, so on and so forth. So that is definitely kudos on that. So let's think in terms of degrees of freedom. And I'm about to greatly simplify what would be several pages of math from a topic called invariant theory. We're going to do kind of a quick and dirty derivation, which is not strictly correct in the most extreme and strict of senses, but this is going to be plenty for our purposes, right? So let's think in terms of degrees of freedom. Okay, so a star field image with D stars, where D is the number of stars in the image, has 2D pieces of useful information for navigation. We're just going to say pieces of info. What do I mean by that? Each star has a line of sight direction which has 2 degrees of freedom, right? Azimuth and elevation, or you could think of it as a unit vector, but the unit vector is 3 numbers with a unity norm constraint, so you still have 2 unique degrees of freedom. I'm just going to say azimuth and elevation for now, or your tangent angles in the image, however you like to think about it. But if you have 5 stars in the image, you have 10 pieces of information, right? Now, a camera, which is free to rotate, has an attitude. And remember, we discussed this all the way back towards the beginning of the semester. And attitude in 3 degrees of, sorry, I already said the punchline. An attitude in 3D space has 3 degrees of freedom. Right? So we have three doth. Right? You've got you could think of it as roll, pitch, and yaw. You could think of it as the 3 unique pieces of information in an attitude transformation matrix, which is 9 numbers with 6 constraints. The 3 unique pieces of information in a attitude quaternion, which is 4 numbers with 1 constraint. However you want to slice it, there's 3 bits of information that you need to tell your attitude, but there's 2 times D pieces of information in the image. And it turns out that an asterism, this is kind of the punchline here, an asterism of D stars has 2D minus 3 invariance under the action of a rotation. Okay, so what do I mean by that? Here. For a single star, and that is D equals 1. 2 times 1 minus 3 is a negative number, right? So there are no invariants. So you're sunk. Okay. For a star pair, D equals 2. Some of you are already doing the math on your fingers. 2 times 2 is 4 minus 3 is 1. That's quick math. There is, proper English, 1 invariant. Right? And that's 2 times 2 minus 3 equals 1. Right, that's our idea there. And then for a star triad, d equals 3, there are 3 invariants. And that is 2 times 3 minus 3 equals 3. Right? And so that is actually what we were already saying, right? So a star pair has one angle, and that angle is invariant. It's going to be the same however you look at it, assuming there isn't some malfunction with your camera. If you have a triad of stars, that's 3 pieces of information or 3 interstar angles. You could also use dihedral angles, right? So we'll talk about that, but we're mostly going to think about interstar angles in this class. So what this means is you actually have a prayer of identifying a pair of stars. You could create an index of star pairs with interstar angles, and you'll say, well, look, here are all of the interstar angles for all of the pairs of stars in the sky. And now we're going to find that exact star pair in the catalog. Or here are all of the sets of 3 interstar angles for all triads of 3 stars in the sky. And now we're going to go find our exact asterisk or our 3 stars in the image in the catalog, right? And so some of you might be thinking, all right, wait a minute, Paul, that doesn't sound very realistic to me. Like there's got to be a lot of star pairs out there. There's got to be a lot of star triads out there. How many stars do you need before you have a unique solution that isn't incredibly close to another unique solution, right? Surely there's some star pair out there where the stars are 10 degrees apart, and there's some other star pair out there where the stars are 10.00001 degrees apart, and that difference is smaller than the uncertainty that you actually carry in your camera measurements. Some of you might be thinking that way. Others of you might be wondering how long we have to be talking about this and when we're going to be done. But those of you that are really on top of it, that's the way you should be thinking. Like, okay, sure, mathematically, you can precisely identify a pair of stars in an image. But what about practically? And we're going to talk about that in the next kind of little chapter here, basically, is how many stars do you need before it is practical? And my recommendation is going to be 3. You can do it with more. You can try to do it with 2, and there's ways to do that. But I prefer to work with triads of stars for identification. So here comes a little diagram just to kind of identify what exactly do we mean by these interstar angles here. So let's say here is your camera, and let's say that you've got almost looks like a projector screen, and you've got a star field image. And let's say that you've got some stars out in the distance. Here's star I, star J, and star K. I, J, K. All right. And let's say that, and here comes my ability to draw. So pretend that's a straight line. There we go. And do one down here. There we go. And the last one is up here. Gonna try that again. Good enough. So here comes some color coding here. We'll use red, green, and blue for now. So we can think of it as here is some distance between stars in the image, which is really indicative of some angle, which I'm going to call theta ij. And then here is another star pair in the image, and we're going to call this angle between them theta jk. And then finally, surprise, surprise, we've got this star pair in the image, and we've got some angle between these, and we're going to call that theta. You can either do ik or ki, right? And an angle is a scalar, so the order doesn't matter, right? So if this is your star field image, and this is your camera, and these are your stars, we've got three angles to work with, and we can deduce those angles very simply from our image processing, right? So lecture 18, we made it to the point where we actually have the line of sight directions to three stars. Well, it's just a dot product to get the angles between them, essentially. It's going to be the arc cosine of, I transpose j, essentially. So it's very straightforward to get the interstar angles. I think the big thing that we need to be thinking about is how do we actually set, because this turns into a database problem, essentially. How do we make that database practical? So questions up to that point, or are people feeling mostly okay with everything we've discussed so far? Okay. So I know it's a little bit earlier than we usually would take a break, but I need to take a restroom break. So we're going to pause for about 5 minutes, and let's say we'll be back at 6:35. And we might take two breaks today, actually, because we're about a third of the way through the material. So we've got a little bit more to talk about. But let's take a break for a minute. I'll see y'all back here in 5 minutes. All right, I appreciate y'all having patience with me here. So let's resume our discussion about star identification, which has now been reduced to an index search problem. Right now, we're starting to think in terms of data structures and databases. So star ID as an index search problem. I suppose I should have used capitalized because this is a section heading. So the problem of star ID becomes an n-dimensional space search where n is 2D minus 3. It's the number of invariants that we're dealing with. So the key point I'm trying to make here is that one can choose to try to identify larger or smaller asterisms. So you can do arbitrarily large groups, or you could do star pairs. I think 3 is the Goldilocks number, but that's my opinion. I'm not going to hold you to that on the homework if you want to try something different. One can choose to try to identify larger or smaller asterisms. And there's going to be consequences either way, right? It's like a Goldilocks problem. So here's something interesting. Higher dimensional spaces with more entries are less crowded. So what does that mean? Well, it was kind of the point that I was getting at before, right? If we think about all of the star pairs, right? There must be some star pair that's exactly 10 degrees, and there must be some other star pair that's 10.00001 degrees, right? And so when we are doing an index search problem in practice, what we're going to return is either a nearest neighbor to the guess that we start with, which our guess could be wrong, or B, all entries within some bounded region around our initial guess, which is also wrong. And that could return several candidates to say, well, look, I really think that my star pair in my image is about 10 degrees. Let's go check the catalog or the invariant index. And the invariant index might have 15 star pairs that are all roughly 10 degrees. And you think, well, gosh, if I knew the exact number to within machine precision and there was no noise, it would be a unique problem. But in the presence of noise and real world perturbing effects, I kind of need some other information to help me identify which star pair those are. Whereas if we're looking at a triad of stars, where we have three interstar angles, now each star triad can be thought of as a point in 3D space. I'm going to draw a picture of this in a minute. And even though there are more star triads than there are star pairs, 3D space is so much bigger than 2D space that whenever you're searching within some region, the probability of two or more matches is lower and lower and lower, right? That's essentially what we're after here. We're trying to get to the point where we have a unique solution. Now, in practice, you might still not have a unique solution, so you need some method of dealing with that. And we're going to talk about two different methods of dealing with that. But hopefully y'all are tracking roughly what I'm talking about. We're going to draw some pictures in a second here. So if you choose star pairs, you have one invariant. Your index is a number line. Find the closest number on the number line to the number that you're starting with, right? Your index is a number line. If you choose star triads, you have three invariants. your index is three-dimensional. Now, you could scale this up. In practice, people only ever try to identify triads or pairs. I wouldn't bother with sets of four, because what ends up happening is you get benefits by choosing larger asterisms in that unique identification becomes an easier problem, but making the index is a harder problem, right? If you're just looking at an index of all pairs of stars, that's going to be way smaller and way easier to search than an index of all triads of stars. So you get to choose whether you want to eat your pound of dirt up front or at the end. But one way or another, there's going to be some pain and suffering involved with the star ID problem. But this three-dimensional search space drastically, can't emphasize that enough, drastically reduces the probability of a false match. Okay, so here's what I mean by this. If you've got, I like to learn visually, if you've got a star here, and a star here, and a star here, so this is going to be a little junior version of the diagram that we just saw from before, right? And you've got some interstar angle here, and you've got some interstar angle here, and you've got some interstar angle here, right? And I guess we'll call these, I should probably label these two, theta ij. This is kind of a, yeah, simple version of the diagram we just saw. Theta jk, and maybe the green one is theta ki, right? Then you could think of this as, when the time comes to actually go check your database, you could think of your database as a three-dimensional space where your first axis is a number line of all the theta ij's, and then your second axis is a number line of all the theta jk's, and then your third axis is a number line of all of the theta ki's. Then every invariant, or every asterism of three stars in the catalog is going to be a point in 3D space. I'm trying to illustrate a point cloud here, right? And when the time comes to search the catalog, you're going to start with some initial guess, but really you're probably going to search some region around that initial guess, and you might find that there's one right next door. So you could either do a nearest neighbor search, or you can do an kind of a region search. And so we could think of this as, and actually this diagram should look a little familiar. This is what I was drawing before, our index search problem. So it's a three-dimensional index search problem where you could think of your first dimension as theta ij, your second dimension is theta jk, your third dimension is theta ki. One unique point in 3D space is one unique set of theta ij, theta jk, theta ki. You are going to be wrong because your image is noisy, but hopefully if you search some bounded region within the index, you only get one, pardon me, only get one return, and that's what we're after. So you might be thinking, so let's get the show on the road. Let's just take all triads of stars and make an index. And to that, I would say, not so fast. Some of y'all might be already noticing the problem with this. There's a lot of stars, and there's a lot of star pairs. It's roughly the squared number. It's like all the star pairs. It's not exactly going to be n squared, but it's going to be, you know, similar to n squared. It's going to be similar to n cubed number of star triads, not exactly. As a matter of fact, if you have a catalog, let's be precise about this, a catalog of m stars and an asterism of d stars, produces an index with M choose D entries. Hopefully you're familiar with that notation. It's like N choose K. In this case, it's M choose D. So if we were to blindly take the entire Hipparcos catalog, so in the case of Hipparcos, which we talked about last class, which has 118,218 stars and star triads. So we're looking at all triads that we can produce. That is 275 trillion triads, which is clearly unreasonable, right? We need some way to pare that number down a little bit. So what can we do? We don't need to consider every star in the Hipparcos catalog, right? We don't have to consider every star in the catalog. So for example, you can limit it to stars that are brighter than apparent magnitude 5.5, which is what I recommend that you do on the homework. That drops us from 118,218 stars to, I think, less than 5,000 stars. It's been a while since I've looked at the code and the intermediate results, but that's a heck of a lot better. So now we're down to 5,000 stars. 5,000 choose 3 is still completely unreasonable, so that we've made some progress, but it's not reasonable for you to do on your computer in the length of time that there is between now and the deadline. So it's like we got to further reduce this, right? We also only need to consider, and this is where engineering comes in, we only need to consider asterisms that would fit in an image, right? So the field of view of your camera is extremely useful information. You could say, well, look, for example, right, e.g., in the case of Orion, right, the Orion optical navigation camera has, I don't remember the exact number, but it's roughly a 20-degree field of view, right? Okay, that's supposed to be the letter O. Roughly 20-degree field of view. So what does that mean? It means there's absolutely no chance that we would ever need to consider an interstar angle of 30 degrees because we would never see both of those stars in an image. You might see one of those stars in an image, but we're looking for star triads where we would reasonably expect to see all three of them in an image. So in this case, we can say theta ij, theta jk, and theta ki should all be less than 20 degrees. So between these two bits of information, we only need to consider stars brighter than 5.5, and we only need to consider star triads or star pairs where the interstar angles are less than the field of view. That drastically reduces the size of our catalog down to something that is actually reasonable for homework 4, which is nice because that's what you're going to need to do. So this is a good pausing point if anybody has any questions. Otherwise, we're going to start talking about the actual index search problem here. I guess that's kind of what we were talking about before, but it's going to get to a little bit more practical. So this is where, if you wanted to, and those of you that have more of a computer science background could rely on data structures techniques. So data structures such as the KD tree, the R tree, and the NDK vector can be used to facilitate faster searching. And my advice would be, if you have familiarity with computer science and data structures concepts, and you want to use those to make your job easier on homework 4, either make it faster to create the catalog or faster to search the catalog, then by all means go for it. I am not expecting a catalog that can be created or searched in real time. So if you want to go the extremely brute force method of just a triple nested for loop and then consider every possible combination of stars, I actually tried that just to see what it would take, and it will require more than 24 hours for your computer to chew on that. But it will also work. So you're going to want to take that into account. If you decide to use a brute force-esque approach to produce your catalog, you need to take into account that you're going to need to let your computer chew on it for a while, like several hours, depending on how you code it up. Whereas, those of you that are more comfortable with some of the snazzier data structures techniques could maybe get this done a little bit faster, but it takes more thinking up front. That is totally dealer's choice. You can do whatever you want to do for homework 4. I'm not going to tell you one way or the other. But let's consider then, once you have a match hypothesis, right? So this is after you've done your search, and I'm going to give you a couple of practical pieces of advice on how I did it when I put this assignment together. But let's say that you've gone through and you've found a triad in the image, and you've checked your invariant index, and you found what looks like a pretty nice match, and you want to make sure that you know that you're right before you just blindly proceed onward, right? So once you have a match hypothesis, and this is a candidate asterism index match, it can be validated by testing additional stars. So hopefully you have more than 3 stars in your image. In the case of homework 4, you have way more than 3 stars in your image. I think you have 1 or 2 dozen stars in the image, which is great. So here are a couple of options, right? And I'm just going to explain all of these at a technical level, and you can code these up however you want to. One of them is pick a new triad containing 2 of the original 3 stars and 1 new star. And then identify that triad. And then you can ask yourself, do the duplicate stars, so let's say you've identified stars A, B, and C, and now you're going to go check stars A, B, and D. Well, A and B were in both of your triads. Do these duplicate stars have the same ID? You can check that. And this actually is part of a technique called the pyramid star ID algorithm. And so, because you can imagine if you take your original 3 stars and then a 4th star, you could do, okay, so there's A, B, and C, and now there's D. Well, you've got triad ABC, ABD, ACD, and CBD. So that gives you 4 triads, which if you think of that in terms of like a shape, that would be a tetrahedron or a triangular pyramid. So that's where you get the pyramid name from. That's the pyramid star ID algorithm. Or an entirely separate strategy, which is equally valid, a little bit slower maybe, is you could move on. So you can compute an expected attitude from your triad. So let's just assume that we're right? You've identified a triad of stars. Let's charge on to lecture 21 and solve Waba's problem. We haven't talked about how to do that yet, but you will be able to very shortly. And let's say, okay, let's just assume that we're right. If that's the case, then we can actually take the entire Hipparcos catalog of stars that are brighter than magnitude 5.5 and project the catalog into the image. project the catalog into the image, basically giving you a synthetic starfield image. So, okay, if I'm right about my attitude, this is the starfield image that I should see, right? And this requires you to use your attitude and your intrinsic distortion parameters. I guess that's a semicolon, right? Because attitude as well as your intrinsic and distortion parameters. And then what you'll find is that many, maybe not all, but many stars in the image should be almost on top of their catalog counterparts. And there you go. So this is a separate method of star identification. And so these, I don't know if this one has a name to it. This is kind of like the guess and check method. But these are the two main methods of star identification that I'm aware of, at least. I personally prefer the second method just because I'm pretty comfortable creating synthetic starfield images, and you can just leverage those tools. It's like, okay, well, we've got a database of all these line of sight directions. Let's just compute what their pixel values would be using the content from lecture 18, right? So in this case, we're starting with line of sight directions. You assume that you know your attitude, and you work all the way through and you find their directions in the local camera frame, and then you distort them, and ultimately you arrive at pixel values for all of those, right? And then you could just go through and say, oh, well, let me find the nearest neighbor in pixel space, and oh, look, there's a star within 1 pixel. I think that's the one, right? And you do that again and again and again, and ultimately identify, which should be several stars in your image, right? So it's not just going to be 3 or 4, it's going to be several, right? So these are two different ways. You can pick whichever one makes more sense to you, whatever seems like it would be easier to code up. This is my personal preference. I like the second method, but you're under no obligation to do it the way that I want you to on the homework. And that's pretty much it. So I have some practical notes for homework 4, and then we're going to take another brief break. And then the rest of the lecture is just prepping us for next lecture, which is going to be very math heavy. But let me just share a few practical notes for you here. So practical notes for homework 4. Okay. So you will either need a star pair index or a star triad index. The triad index takes longer to make, takes longer to search, but is more reliable. That's the trade-off. This is what I did. Maybe not the smartest way to do it, but this is what made sense to me. I made a huge matrix. Where each row has index number, Hipparcos ID. So this is HIP, is the Hipparcos identification number of the ith star, the line of sight direction of the ith star transpose, so that's 3 numbers, the Hipparcos identification number of the jth star, and that's a J, the line of sight direction to the jth star transpose, the Hipparcos identification number of the K star, line of sight direction to the K star transpose, and then theta ij, theta jk, theta ki. So I had that many, that was one row, and then there were as many rows as there were valid triads of stars. That was my method. Again, you can do your own thing. I was also careful not to double count triads. And so you can think of it this way: triad A, B, C, and triad B, C, A, and triad C, A, B are all the same thing, right? If it's the same stars, you don't need three entries, right? That's one thing you can think about. And I used stars that are brighter than magnitude 5.5 and where the interstar angle is less than 20 degrees. When searching, make friends with KNN search in MATLAB, or the equivalent in Python if you're a Python person. And if you're working with triads, which I did, for an image triad, you'll need to search 6 times to account for permutations. So you've got 3 bright spots in an image which you think could be stars, but you go, okay, well, let's call these I, J, and K, and we're trying to match them to A, B, and C. Well, you've got IJK, KIJ, KJI, KIJ. You can think of it, there's 6 possible ways to group your 3 stars, and you're going to want to essentially search 6 times. And you'll look for, after your 6 searches, the best match that you've got, or maybe you've got a few really good matches. And then you'll take those and you can double check those either using the pyramid method or using the other method that I outlined. But I would say that this specific topic, really more than anything else we've covered so far in this class, is very open-ended and the devil's in the details. And as you go to code this up for your homework assignment, you will meet the devil in the details, and it's going to take you a while. I would have to estimate that this is going to be about 60 to 70% of the homework in terms of time that you put into coding and debugging. Whereas image processing to find your line of sight directions and downloading and processing the Hipparcos catalog, each of those should take, an hour or 2 tops, unless something has gone really wrong. Maybe 3 hours, but this is going to take you a minute. And then finally, the next step, which is the attitude estimation problem, is going to be very straightforward after we go through the math next lecture. So there is more content, but I want to pause and give you another break. And then we're just going to go through about a page of math, maybe a little bit more than a page on, no, it's pretty much just a page of notes on the uncertainty that we have in a line of sight direction, which is going to actually the uncertainty, what we call your bearing error in a star line of sight direction, is going to cascade to the error bounds with which you approach your index search. You go, well, I'm really only sure about these interstar angles to within 1/10 of a degree. Then that kind of gives you the size of the bubble that you want to search when you go into your index. So we'll talk about that after a 5-minute break. So it is 7:04. Why don't we come back at come back at 7:10. And I'll stick around during the break in case y'all have any questions for me.
Hi, I had a question about uh, processing the image for the homework.
Sure, for the lecture 18 material.
Yeah, I don't know. When I use the BW con comp thing, it tells me there's like 300,000 objects in the image.
Ooh, okay. So that's the BW comp. Are you feeding it a black and white image, or are you feeding it the regular raw image?
I was feeding it the regular raw image, but like when I do feed it like a binary image, it comes up with like even more objects in the image.
Interesting. Okay, so what I would recommend is you don't run BW concomp on the raw image. You run it on a all black and white image, which you create as like an intermediate step. And that black and white image is every pixel in the original image brighter than some threshold becomes 1. And every every pixel in the original image dimmer than some threshold becomes 0. And so this gives you all of the bright spots. And so your BW concomp will give you what are called connected components. And then you can go back and use those to do centroiding on the original image. But did you do the thresholding step, or was that, because I think it's important to do that before BW concomp?
I mean, I did a thing where it just does image to black white, and then you have like the picture, and then I guess the level you have.
Okay, so I
Like
think
I
that's the
did,
step that's missing. Yeah,
yeah,
so
like I
you're gonna
did do that, but I still came up with like 300,000 things.
no, yeah, I think what you're missing is a step that looks like this. It's going to be something like temp image is equal to original image. I'm assuming you called your original image img. Img greater than thresh, semicolon. And what that does is it creates a separate matrix of numbers that are all ones and zeros. And it's a 1 everywhere your image is greater than your threshold, and it's a 0 everywhere else. And then you do BW concomp on your temp image. And I think that's what's going to save you, because I think otherwise, yeah, it's going to come back with like, I'm sorry, this is so many connected components that you're going to fry your computer trying to process all these. And so, yeah, it's like we're trying to avoid that. But I would recommend this intermediate step and see what you come up with. You can even tab out and try that right now if you want to. We've got a
Like,
couple minutes before we start back up.
so am I not doing like image to black white, and then like it
Um,
and, like I put it in the chat. I'm using like that,
oh,
and that's like it
maybe
takes in the picture, and then I guess the
maybe that's the
level.
same thing. Yeah, I didn't even consider that. So what did you use for level in that case?
Level, I got the uh I'm pretty sure it was like the 10 over 255. It's like 0.03 something.
Okay, so then that is probably the same thing as what I wrote out, but that's just using an inbuilt function, which is fine. So I think what you're liable to run into then is your image out of 1 or is your image out of 255? Because and you could just look at like what is the max value of your image. And if you do that and it returns say 255 or something like 250, then that means it's working with those numbers. Whereas if you're giving it a threshold that's less than 1, it's going to think that every single pixel is brighter than 1, right? Because it's just a scale question. Are you talking about
Wait,
numbers between 0 and 1? Or
how do you check the
you could try something like max of image open parentheses colon close close. What this does is it turns image into a one-dimensional vector, and then it'll give you your maximum value.
you said open parentheses what?
Just like what I have written here, the max of image open parentheses colon close parentheses. So instead of giving it an individual element, if you pass the argument colon, what it will do is it will say, oh, well, I'm now looking at the entire image as a list. Because otherwise, if you just say max of the image, it'll give you the row with the maximum value because it's two-dimensional.
Okay, it says the maximum is 247.
Okay, so in that case, you're working with an image that goes up to 255, but you're giving it a threshold that's less than 1. So what if you tried the exact same thing that you did before, but now you are working, instead of putting in 10 over 255, you just put in the number 10.
Just 10.
I think that would probably do it.
Um, it says that the number has to be between 0 and 1.
Oh, interesting. Well, in that case, what I did was I decided that I wanted to work with numbers between 0 and 1. So you could have another command up towards the top that just says image is double image divided by 255, like that. That is an extra line that I have in my code. And that means that now every pixel, even though it still has a bit depth of 8, so it can only be one of 255 numbers, it is now a number between 0 and 1. And so I would try that. You're just kind of recasting your image. It also moves it from, I believe it loads in as an unsigned integer, and you want it to be like a regular old double matrix that you can work with a little bit more easily.
Wait, so then I don't, wait, if I do the double that divided by, do I not need to change it to black white using that command that I sent?
Well, so then you still need to go back to using the black white command. All we're doing now is recasting the image as numbers between 0 and 1 rather than numbers between 0 and 255. You'll still need to use image2 black white, but then your threshold value would be 10 over 255 rather than just 10.
Okay.
All right. I'm gonna keep on going because that's our 5 minutes. So I want to talk about
Okay.
the next thing, but stick around after class if you want to talk a little bit more about this, okay?
Yeah.
All right, cool stuff. So here we are. Welcome back, everybody. And let's talk about the next thing, which is a topic called bearing error. Or actually, wait, we talked about, you know what? I got my wires all crossed. We already talked about bearing error. We're talking about something else, which is a star tracker measurement model. We already talked about bearing error. Sorry about that. Star tracker measurement model. All right. So once the star ID problem is solved, we have an attitude estimation problem. So this is really a preview for next lecture, right? We have an attitude estimation problem. So we will denote the ith star line of sight direction in the camera frame as UIC hat squiggle. So U is just our letter that we're using. I as in it's the ith star, C as in it's the camera frame, hat as in it's a unit vector, and squiggle as in it's noisy. So this is what we measure. We will denote that same star. So we're assuming we've solved the star ID problem. The ith star line of sight direction in the catalog frame or in the inertial frame, think International Celestial Reference Frame, as UII with a hat. It does not have a tilde because it's considered to be the perfect measurement, so it's not noisy. So this is, the top is measured, the bottom is catalog. And what is the relationship between these? Well, it looks like this. UIC hat squiggle is equal to some attitude transformation matrix from the I frame to the C frame, UII. Actually, you know what? I lied to you. There's no squiggle on this equation. Sorry about that. So this is the perfect, in a perfect world, there is just some attitude transformation matrix, which maps from UI to UC. But in the real world, it looks a little bit more like this. UIC, this one has the squiggle, is TI to C, UII, and guess what? There's noise like that, right? And so this is where our epsilon, where epsilon, which is a vector, is measurement noise. With, supposed to be a W, with the expected value being 0. And we want to learn a little bit more about the measurement covariance, because when we get into our attitude estimation problem, we're actually going to care quite a bit about the star tracker measurement covariance, and that's what we're building towards here. Now, we should be clear that we seek the attitude transformation matrix T from I to C, which you could think of this as inertial to camera. And this is what I gave you actually on homework 3, right? You had the quaternion from the ICRF frame to the star tracker frame. That was a given. Now we're actually trying to build that by an estimation problem, essentially. So let's go back and talk a little bit more about this noise, though. So this epsilon, because, so you might have noticed this, because UIC and UII are both unit vectors. Kind of seems a little bit weird that we can take a unit vector, rotate it, and then add something, and then get another unit vector. It's like, wouldn't adding something in general violate the unity norm constraint unless there's something special about the noise? And there is something special about the noise. That noise is perpendicular to the measurement. So it must be that epsilon transpose UIC is 0. You can think of it this way. There's we can illustrate this on a diagram here. This might make a little bit more sense. So let's say we've got a coordinate system. Let's say you've got a unit sphere. And let's say that you've got a point on the unit sphere, and then that same point on the unit sphere, but after a little bit of noise. And let's kind of zoom in on this a little bit here. So we should be clear, this is a unit sphere. And if we scale this up, here's what we're actually seeing. There's some vector UIC with noise, which is very similar to the vector UIC without noise, where all of the noise is right here. And this is a right angle. You can think of it as it's just tangent to the surface of a sphere. And you might be saying, well, even then, now we're still, if we're adding a number, then we're going to be, wandering off the unit sphere. It's like, well, to first order, this is largely the case, right? Epsilon transpose UIC is equal to 0. We're saying that our noise does not lengthen or shorten. It simply moves it to another spot on the unit sphere. That's essentially what we're going for. So we can build a measurement covariance matrix can be built using the Quest model. So you can go read about the Quest model. It stands for Quaternion Estimator. Okay, so what exactly do we mean by this Quest model? So UIC, the noisy measurement, is a rotation, or in this case, a passive rotation, times UII plus epsilon. And you could just think of this as UIC with noise is UIC without noise plus epsilon. Okay, well, our measurement covariance is going to look like Ri. That is the expected value of our noise times our noise transpose. And this is where we're going to skip a step, and you're going to take my word for it because we only have so many hours and minutes to talk about this. This is our bearing error squared times UIC cross product matrix times UIC cross product matrix transpose. Okay, so this is where we're going to skip a couple steps, and we're going to go, if you really want to read more about it, you can go look on Google Scholar on quaternion estimator or the Quest measurement model. We're going to skip the step for now, and this is actually going to simplify nicely. So this is our bearing error, by the way. Okay, because this, what might look like a mathematical nightmare of cross product matrix times cross product matrix transpose, well, let's actually run that to ground really quick. So what is that going to look like? UIC hat cross UIC hat cross transpose. Well, what is that? Well, it's going to be, remember, 0, negative U3, U2, negative U1, positive U1, negative U2, positive U3, 0, 0. And then that's going to multiply the same thing transpose. So 0, positive U3, negative U2, positive U1, negative U3, positive U2, negative U1. And if we multiply that out, we get this really neat pattern. We get U2 squared plus U3 squared along the diagonal, U1 squared plus U3 squared, and U1 squared plus U2 squared. And then the off-diagonal elements look like negative U1, U2, negative U1, U3, negative U2, U3, and it is symmetric. Negative U1, U2, negative U1, U3, negative U2, U3. Okay, neat pattern. What is that? Well, it's just this. It is the identity matrix, 3 by 3 identity matrix, minus UIC transpose. And if you want to, you can actually go through element by element and convince yourself that that is the case. So skipping some steps then, what that basically means is the Quest model gives us the measurement covariance matrix Ri is approximately equal to sigma I squared times the identity matrix minus UIC transpose. Okay. Now the problem is you can't invert this, right? If we're trying to invert this measurement covariance matrix, it's rank deficient. So this matrix is rank deficient. So we use the pseudo inverse. And that is Ri with a dagger is 1 over sigma I squared, and then everything else is the same. So we're just dividing instead of multiplying. And then transpose. There we go. And so then, if we wanted to, we could build a block diagonal matrix. So thus, actually, you know what? That's probably good enough on that for now. That's good. We're gonna stop there. I think that's a good natural stopping point for today. The reason that we mention this lecture instead of next lecture, because this does not have very much to do with star identification, is that next lecture is already full. Like it's going to take us quite a bit of time to get through the material, and this is kind of just a necessary setup. So later, next class, we're going to be waist deep in some derivation, and we're going to need the measurement sensitivity matrix, or sorry, the measurement covariance matrix, which is this R, and we're just going to plug it right in, and we're going to say, don't you remember last class when we talked about that? So that's the idea. Anyway, y'all have certainly had plenty of patience with me today. I appreciate that. We're going to stop now, and y'all are dismissed, but I'm going to stick around to answer whatever other questions that you might have. So I appreciate you, and I'll see you on Thursday.